All right, thank you. So again, uh, so this is the difference. Is it working? I don't know. Okay. So the difference between the other studies, we just choose aluminum in this time, so to understand the physical properties. So the background is almost the same, so we will make some devices to make sure what kind of elements, what it does what. So I'm going to try to define the crystal structure, synthesizing method, crystallization, XRD, SEM, it has the optical properties, and I'm going to show you again the optic results. So here the aluminum, copper aluminum O2 is really very important, and it is actually studied more. And we always have the other properties when we add some elements in it. So it has, the potential interest in thermoelectric properties too. So we just try to understand first of all the physical properties, and then we are going to add some more elements to improve the physical properties correlated with the thermoelectric properties. So this is a kind of crystal structure schematic form. The crystal structure of the copper atom O2 is rhombohedral unit cell with the space group of R-3m. So in synthesizing of copper atom O2 is we use solid-state reaction method. We used an open-air heat sinterate. We applied that kind of system by increasing the furnace temperature 4 degrees per minute. We finally reached the temperature 1100 degrees centigrade, and the sample was kept at that temperature for 1.5 hours. Then the furnace was turned off for self-cooling without a program. Degrees. So here, okay. So here we have XRD. To understand the phases, if it is there, so we just calculated the lattice parameter as A equal to 0.2858 nanometers, C is like 1.689 nanometer. The particle size was calculated also as 40 nanometer using the Weishire equation. As SEM image, the SEM image of the copper aluminum oxide sample is synthesized by the solid-state reaction method. We see the 2 micrometer magnification given the figure. The particles in the image are almost separated from each other, and the melting doesn't become actively effective with the annealing temperature. We also got the EDX analysis, so to understand the stoichiometric ratio of the elements in the system. So atomic percentage are given as the exact copper aluminum O2 composition. Here, the magnetic properties, to understand first of all magnetic properties, what happens when we prepare the sample at 1100 degrees centigrade. At low and high temperatures, weakly non-linear magnetization curves were observed. You see here we use different kind of measurement at 10 Kelvin, 50, 100, from 150, 200, 300 Kelvin. So, so we just see some ferromagnetic behavior, but I don't want to say such things. So I will tell you later what's going on in the system in the next slide. Maybe here you will see the corset field is changing by the temperature. This is the table of understanding constant measurement temperature from 10 to 300 Kelvin. So we have remnant magnetization value, saturation magnetization value, and the corset field magnetization value. You'll see here the corset field is a little bit fluctuation. So there is a couple of reasons. One of them is maybe temperature, we can say, in this fluctuation. The other parameter, saturation magnetization, is almost giving us same, let's say, similar results. So the remnant magnetization I gave in the table, you see, like it is almost decrement in tendency. Okay. So first of all, what we did here, The samples present MH measurement at 10 Kelvin, and the line given by the red color present the fitted Bruin curve. The magnetization curve at 10 Kelvin had fitted with the envelope model. The figure manifests a trace of ferromagnetic contribution due to either the role of impurity or residual ferromagnetic contribution. No such ratio was observed by the applied magnetic field between minus plus 6 kilohertz state. The overall behavior is typical ferromagnetic actually. The reason behind this is addressed to copper 2 plus the 9 electronic configuration in the structure. So what we had more is a kind of the zero-field cooled magnetization result. The temperature-dependent magnetization of the copper aluminum oxide sample in zero-field cooling property was presented in the figure you see in the range of 0 to 300 Kelvin. As seen in the inset, we have inset figure right here. Especially 600 Kelvin, we have an antiferromagnetic short-range order, which was the same in the literature. This is right here. And the reason behind this should be the preparation method, which causes oxygen vacancies, especially for the solid-state reaction method. That the ferromagnetic short-range order revealed at 600 Kelvin in the inside of the figure ascribed to a mixed state of copper 2 plus together with copper plus with a high amount of oxygen vacancies we have in the system. So we also got some PL measurements to understand if we have some oxygen and other kinds of vacancies. This is a kind of our PL measurement. We have 1 to 9 peaks. These are emphasizing different results here. Here in the table we shows the oxygen vacancies, and the other copper shows copper vacancies here. In the region, in the UV region, we have a sharp transition peak ascribing to nearby age transition. We observed that peaks between 362 and 376 nanometer for copper aluminum O2 sample. MBE emission is caused by excitonic transition between electron and holes. The stronger UV emission of the sample, the higher crystallization quality and the fever detects occur. When compared to other studies in the literature, it appears to have a higher crystallization value. It means that sample growth annealing temp is suitable for crystallization quality. So we also have the second dominant and the fourth emission peak is a visible region known as deep level emission. Consists of blue, green, yellow, orange, red. This one right here, 6, 7, 8, and 9 in PN measurements. Alright, deep level emissions are just impurities or defects such as copper vacancies, aluminum vacancies, and oxygen vacancies. Alright. So we also, calculated if our, copper aluminum oxide band gap energies are the same with the literature or not. So this is a, measuring method to see your result, exactly even as the same material. You find direct and indirect band gaps here for copper aluminum 2 nanoparticles like 3.36 and 3.64 and 2.2 and 2.88 electron volt respectively. In the result part, the direct reaction of the chemical was subject to redox reaction, and we have investigated the extraordinary phase. Particle size was calculated approximately 400 nanometers. We also calculated direct and indirect band gaps, as shown in the value right here. Additionally, the role of impurity and residual ferromagnetic contribution might be possible in the system due to exhibiting a trace of ferromagnetic behavior. So, the magnetic field dependent magnetization curve at 10 Kelvin was fitted to M. Brouillon model and showed that the dominant ferromagnetic contribution existed. So, the zero-field cooled curve manifested that the concavity at almost 600 Kelvin was due to an antiferromagnetic short-range order, and this fact is the reason of oxygen vacancies revealed by PL results. So we again, the system is used marginal distributed, but actually we're going to change the dopant effects. First of all, this is copper aluminum O2 is a starting material. In the literature, N-type material is used as technology application, but P-types are not used much. So due to hole mobility, low hole mobility, so the reason behind we use this and we will keep going working with the P-type material is low cost and to make a device using this system. Okay, thanks so much.